Bismillahirrahmanirrahim. In this lecture, we are going to speak about the homogeneous linear systems of differential equation and how to find the general solution for such systems. First of all, define the homogeneous linear system of differential equation. It is a system, linear or first order system is written as x prime equal to a x. This is the general form for the homogeneous system. This a prime equal to a x, where a is an n by n matrix. And x prime, this notation means that is dx by dt. Our variable here, or independent variable, is t. So x prime equal to dx by dt, or x prime equal to ax is the homogeneous linear system or first order system. And A is an n by n matrix of constants. In this system, we are looking for solution for this differential equation, or for this system of the form x to be a vector written in this form. It is equal to k1, k2, kn multiplied by e to power lambda t, or it's equal to capital K e to power lambda t. So we are looking for a solution of this form. Now let's assume this is the solution. Then if we differentiate, x prime will be k lambda e to power lambda t, which is equal to ax, but x can be written as k e to power lambda t. So if we divide by e to power lambda t, I will have k lambda equal to a k, which that can be written as a minus lambda I multiplied by k equal to 0. So we are looking for this type of matrix, and we need to find the determinant for this one. To find the values for this lambda, we have to write determinant of a minus lambda equal to 0. And the solution for this one will give me something called the eigenvalue of the given matrix. So the constant lambda is called the eigenvalue. And the vector k is called eigenvectors or eigenvector. So we have two things. We have eigenvalue, which is that will be the solution for the characteristic equation. The determinant of a minus lambda I equal to 0 is called the characteristic equation. And the solution for this equation is called eigenvalue. Then we are going to use this eigenvalue to find the corresponding k or the eigenvector. So we have eigenvalue and we have an eigenvector. Now for this equation, we have three cases. The first case that if we have distinct real eigenvalue, this is the first case. Second case, if we have repeated eigenvalues, and the third case, if we have complex eigenvalues. In this lecture, we are going to speak about the distinct real eigenvalues. Suppose that we have lambda 1, lambda 2, up to lambda sub n be n distinct real eigenvalues for the coefficient of, or the matrix A. Then, for each eigenvalue, we have eigenvector. Then we have k1 or k sub 1, k sub 2, k sub n be corresponding eigenvectors. Again, the eigenvector is the vector that satisfies this equation, or this one. Then if we have distinct real eigenvalues, then the general solution for the system will be written as x equal to c1 k1 e to power lambda 1 plus c2 k sub 2 e to power lambda 2 t up to C sub n k sub n e to power lambda sub n t. This will be the general solution for the given system. For example, suppose that we have this system and we need to find the general solution. We have dx by dt equal to x plus 2y and dy by dt equal to 4x plus 3y. And we need to find the general solution. So in the first step, I have to find the eigenvalues. Then in the second step, I need to find the corresponding eigenvectors. So if you write this matrix or the system as in the matrix form, it will be x prime equal to, the coefficient will be 1, 4, 2, 3, multiplied by x, where a is like written x prime equal to a x, where a is given by 1, 4, 2, 3, and x is equal to x and y, the variables of the system. Now I need to find the eigenvalue. So I need to find the determinant of a minus lambda I. This is equal to 1 minus lambda, 2, 4, 3 minus lambda. A minus lambda, we know that I is diagonal matrix. 1, 0, 0, 1. So if you multiply by lambda, it's like we are multiplying this one. Lambda there and another lambda. So we are just subtract lambda from the main diagonal. Now the determinant of this one is equal to 1 minus lambda multiplied by 3 minus lambda minus 8, and this must be equal to 0. Open the bracket and try to find the solution for this characteristic equation. I will have, we multiply, I will get lambda square minus 3 lambda minus lambda plus 3. Just open the bracket, we have this equation, which can be written as lambda square minus 4 lambda, 3 minus 8 is minus 5, equal to 0. By factoring, this can be written as lambda minus 5 multiplied by lambda minus 4 plus 1 equal to 0. This will give me two solutions. Lambda 1 equal to plus 5 and lambda 2 equal to minus 1. So I have two distinct real eigenvalues. Now for each one, we'll have corresponding eigenvector. Just choose take the first one. For the first one, for lambda equal to 5. We have the equation A minus lambda I k equal to 0. So we'll have, it is A minus lambda. We go back, A is equal to 1 minus 5 and 3 minus 5. So 1 minus 5, 2, 4, and 3 minus 5 multiplied by k, which is equal to k1 and k2, equal to 0. 1 minus 5 is equal to minus 4, 2, 4, 3 minus 5 is minus 2, multiplied by K1 and K2 equal to 0. So minus 4 times, so this writing the system in this form, minus 4K1 plus 2 K2 equal to 0. Second equation is 4 K1 minus 2 equal to 0. From this equation, I can find the relation between K1 and K2. So we see that K1 equal to 1/2 K2. Same thing from the second equation. So we have this relation. K1 equal to 1/2 K2. Which means that K, which is equal to K1, K2 is equal to K1 equal to 1/2 K2 and K2. We can take K2 as a common factor outside. We have 1/2 and 1. Now this 1/2 and 1 is my eigenvector. So we can say that the first solution, which is x1, equal to K multiplied by e to power lambda t, which is equal to 1/2 1 multiplied by e to power 5t. So this is the first solution. Second one, we found it for lambda equal to -1. Now for lambda equal to -1, a minus lambda I k equal to 0. This will give me 1 minus 1, or this minus lambda will be 2, 4, 2 and 4. Or it is 1 minus lambda. I can write it as 1 minus -1, 2, 4, 3 minus -1, multiplied by K1 and K2 equal to 0. This is equal to 4, 4 multiplied by K1 equal to 0. Or it is 2K1 plus 2. K2 equal to 0. Second equation, which is 4K1 plus 4. K2 equal to 0. From this, we can find the relation that is K1 equal to minus K2. So the eigenvector will be, it is K1 and K2, which is equal to K1 equal to minus K2, so just replace as minus K2 and K2. Take K2 as a common factor, we'll have -1 and 1. So this will be my eigenvector. So x2 in this case, that is K multiplied by lambda t, which is equal to -1, 1 e to power minus t. And the general solution is x equal to c0 x1 plus c1 x2. Or it can be written as x equal to c0 1/2 and 1 e to power 5t plus c1 minus 1 e to the power minus t. So this is the general solution for the given homogeneous system. So again, to find the general solution, we must, or in the first step, we have to find the eigenvalues. Then for each eigenvalue, we have to find the corresponding eigenvectors. Then we can write the general solution as C1 or C0 times x1 plus C1 x2. So this is the idea for finding the general solution for system or homogeneous system of differential equations.